Your Excellency, honored speaker, Dr. Mourou, dear guests, students, and colleagues, it's a great pleasure for me to welcome you to today's Ørsted Lecture with the distinguished 2018 Nobel Laureate, Professor Dr. Gerard Mourou. Welcome. Dr. Mourou will be speaking to an almost full auditorium, or at least as full as we can have them these days. More people will be watching directly on our YouTube channel and will also have the benefit of seeing the lecture online, so to speak. I should also assure all of you that the auditorium has been cleaned before we came, been disinfected, so you can safely sit in your seats with a safe distance to your neighbor. Dr. Mourou's invention of chirped pulse amplification has been a revolution in high-intensity ultrafast laser science. It has accelerated the evolution of technology to a stage where it now seems within reach to address even the highest energies in physics with light. This would not have been possible without his Nobel Prize invention. And today we are looking forward to hearing much more about this in Dr. Mourou's lecture. Here at DTU, we use the chirp pulse amplification principle every day in our laser laboratories, where intense femtosecond laser pulses are used directly or even for generation of new light across the electromagnetic spectrum. We use femtosecond light to record snapshots of physical processes with femtosecond time resolution. Light that has its origin in chirp pulse amplification is used both in science and for technology, from the exploration of electron motion in nanostructures on the fastest timescales to real-world engineering applications including thickness measurements of ice and other materials, in the search of secrets hidden under the surface of paintings and other artifacts from our cultural heritage, and in spectroscopic identification of chemicals. Of special interest to us here at DTU is the fact that Dr. Mourou was the first to demonstrate filamentation of femtosecond laser light in the atmosphere. This intriguing effect allows, for example, lossless propagation of intense light in the form of laser bullets over kilometer distances. And at DTU, we use laser filamentation for efficient generation of light across the terahertz and infrared regions. Clearly, as these few examples show, at DTU we are deeply indebted to Dr. Mourou for his seminal contributions to laser science and technology. And we are honored to have you here today, Dr. Mourou, for this Ørsted Lecture. Indeed, in this special year, where we are celebrating the 200-year anniversary of Hans Christian Ørsted's discovery of electromagnetism. The very same Hans Christian Ørsted on whose initiative DTU was founded in 1829, with indeed inspiration from your university, the École Polytechnique. Your presence here testifies not only to excellence and groundbreaking curiosity, but also to the importance of international collaboration, to the strong ties between our universities and the presence of history. I will now leave the floor for you to start your Ørsted Lecture. After the lecture, there will be the possibility of questions from the auditorium and even questions from the YouTube channel watchers. And this will be administered by Professor Teitsch Wegge after Dr. Mourou's lecture. But please, Dr. Mourou, I invite you to the scene to shed light on matters.
Thank you. Thank you very much, Rasmus, for this kind introductions. It's really truly a pleasure to be here, okay? And particularly, to celebrate this 200th anniversary of the discovery of Ørsted, foundations of electromagnetism. I mean, we all, electromagnetism is everywhere, right? Including in lasers. And so it's really a pleasure, as I said, to be here with you, and also to celebrate with you. I mean, my Nobel Prize, was given to me exactly 2 years ago. You know that next Tuesday, okay, next Tuesday, which I think is the 6th, at 11:45, okay, you will know who is the next Nobel Prize winner, okay? And I always remember this moment, where I was going to the pool, because I like to swim, and every noon times, I'm going to the pool, okay, swimming. And when my secretary ran after me and said, Gerard, you have someone, you have a call from a foreign country, okay, and you should take it. So I didn't go to the swimming. I just went back to my office and picked up the phone, and here was the chairman of the committee, Nobel committee, which was announcing me that I had the Nobel Prize. I was at Nobel Prize for 2018. And so I was ecstatic, of course, it was great. And he said, but it's not over yet. You are going to share it with your grad student, Donna Strickland. And that was, I knew that very, very few women had the Nobel Prize. But I didn't know that it was that few, okay, because Donna was the third one. We had Marie Curie, Maya Gopper-Meyer, and Donna Strickland, okay? So that was, for me, at the same time, I was receiving the Nobel Prize, and also I was told that you are the first advisors, basically the first faculty who had a woman Nobel Prize winner. So it was, the day, was complete, But I didn't go to it was complete, but I didn't go to the pool, because when you get the Nobel Prize, immediately you get phone call. You cannot, you don't, you have to go through this, to understand what it is. You have phone calls, hundreds of emails, and so on, and the press, and this and that, and it was okay. So that was really, that was exactly 2 years ago, okay. And I'm pleased to be here to celebrate it with the Ørsted Lectures. So, here we are with Donna, okay, and it was a fantastic time. So let me talk about lasers, Of course, it's about laser, what I'm going to tell you about. So, if you don't talk about laser, you have to talk about these inventors. So first, at least the first guy really to make the laser work, because really the inventor was Charles Towns. But the first one who made it work, it was very, very difficult. It was 2-3 years where people was working intensely to trying to make the laser work, okay? And it was this young fellow coming from Stanford, and we had the idea to make it work, because he didn't follow the recipe from Towns, because if you had followed the recipe upon that, we will still be looking for the laser. Okay? No, he made a completely new use absolutely a completely novel idea. I think instead of using gas, he used solid. That's the reason that with the first lasers, was solid state. It was a ruby lasers, and so on and so on. So it was great. I mean, it was great in a sense, but what was not great is the fact that people argued a lot about whether or not Mayman, had this laser work, because it was the idea was Charles Towns, and so they argue a lot, and of course for the number of years, Mayman was not really recognized. In fact, he didn't get the Nobel Prize. The Nobel Prize was given in 1964. And everybody thought it was going to be Towns, Shallow, and because Shallow was working very, very closely with Towns, and Mayman. But then, at 11:45, it must have been a Tuesday, it was, in fact, it was Towns, but it was also Bazov and Prokhorov. No Mayman. And that was kind of pretty sad because, anyway, sometimes, physics is hard on you. Okay, so anyway, so here we have Mayman, holding a ruby laser. Ruby laser was really a very, small gizmo at that time. It was incredibly. A student told me, how after all the CPA, it's pretty simple. Yeah, it starts always very simply. This is the example, and created, and also Ørsted, was very simple, just a simple piece of copper, I guess. I wasn't there, and some magnetic needle, and then boom, it revolutionized the field of physics. Okay, so what is exciting, so for me, I was captivated by the laser. I mean, I was very, I started my research in 1967, so it's only 7 years after, so it was after Mayman's demonstrations. So it was quite new, but I immediately, when I walked in the lab, that my advisor showed me a first laser, which was quite ugly, I have to say. I knew this is what I was going to do. Okay, all my life, and it's what I did. So anyway, so what is very exciting with laser is, the way, the immense number of applications you have, okay? And just to describe, I took 2 big examples, okay? With lasers, which emits, of course, at 1 eV, it was 1 micron, it was, at that time, it was ruby lasers and so on. But it's about 1 micrometer light. It's about 1 eV light, okay? What you can do, you can now slow down atoms almost to a rest, okay? And reach temperatures which are incredibly low, okay? Temperature, we are just only, micro electron volt in temperature. It would be really maybe 1,000th of a degree. Just above the absolute zero, okay? Very, very, very low. And that opened up, of course, the field of slow atoms, okay? Field of cold atoms. On the other hand, so, one limit, of course, is to stop atoms, or particles. The other limit is trying to reach the speed of light, because you know that we cannot go over the speed of light. And so we can see these two extreme things. We can slow down atom almost to rest, so velocity 0, or we can accelerate particles to the speed of light. Okay, this is quite amazing, and with the same kind of with light and with EV light. And then, of course, as you are going to see, with things that we can do is immense, and we can really now accelerate physics, accelerate particles, you know, going into nuclear physics, cosmology, nonlinear QED, and general relativity. I mean, the field, you know, is completely immense. Okay. So this is a laser. Okay. This is a laser which is used, for instance, for people in cold atoms. So there's a lot of application. It's a CW laser. It's continuous wave laser. But there's also the other type of lasers, which is a laser which is really putting out short bursts of light. Okay, the burst of light can be extremely short. Okay, they are in femtoseconds. You know, a femtosecond is a billionth of a millionth of a second. Okay, so that's pretty short. Okay, but now we are in the attosecond, which is a billionth of a second. Okay, it's pretty short. Now you are going to say, well, what are you going to do with this? This is absurd, you know, with using light, very short bursts of light. Well, there's two big applications. If you have very, very short bursts of light, you can really do very high-speed photography. Okay, here you have, you know, these famous pictures of Egerton, you know, showing a bullet going through an apple. Okay. Well, of course, we don't do that with laser, but we prefer to look, for instance, at motions of atoms or molecules and these kind of things. Okay, and we can do it. But the other things that you can do with a very short burst of light is you can produce extremely high peak power. Because power, you know, is energy, and you can see that you have this karateka, you know, which is breaking, you know, a pile of bricks, okay? And so what is it doing, of course, is trying to, you know, basically deliver is the energy in the shortest time possible. And then you can do these incredible things. You can break bricks, you know, like this. But it's the same idea. But this time, we are not going to do that with, you know, we are going to produce now light, but it's going to be, you know, electromagnetic lab energy, okay? And we can now, because we have this very, very short pulse, even with 1 joule, which is nothing, you know. For your breakfast, you eat millions of joules, okay? With 1 joule, but if you deliver this 1 joule in a femtosecond, you are producing peak power in a petawatt regime. Petawatt regime is 1,000 times the total power in a global grid, in a world grid. 1,000 times, okay? But of course, for a femtosecond, not CW, of course. So this is the type of things already we do. But now, you know, we can produce this light with this type of power. Now, what are we going to do with that? Okay, now that's one thing. If you focus this enormous power, you know, on a very small spot, which is limited by the diffraction, that is the wavelength of light. The spot size is the micrometers. Well, you can produce light pressure of light, which is immense, you know, which corresponds to maybe 10 million Eiffel Tower on the tip of your finger. Okay. So, and this is with light. Okay. So this is really fascinating. So now there's one thing is, when we were able with Dana to demonstrate the CPA, then we open up a new regime. Before that, basically, lasers were in atomic physics. We were dealing with atoms, okay, at that. And it was what we call EV regime. Now, that we can produce this phenomenally high peak power, we can go in a subatomic regime. We can really address TeV events. Okay, so we are going to talk about nuclei, protons, electron quarks, and so on. Okay, so this is, of course, is a completely new regime. Okay, it's what we are going to talk about, most of it. So here is the story of intensity as a function of years. Okay, when Mayman demonstrated these lasers, this intensity, which is expressed in watt per square centimeters, the intensity was in 10 to the 8 watt or so per square centimeter. It was weak. But it was enough to demonstrate for the first time nonlinear effect. For the first time, we were able really to produce, from red light, we could produce a beam of green light, you know. That was because we were, you know, driving the electrons, you know, in such a way that, so that happened, you know, in 1961, you know, by Peter Franken. Then, I mean, now you had also a new type of laser, Q-switch laser, mode locking laser, and so on. And so we were climbing this curve of 10 to the, in watt per square centimeters, up to 10 to the 14 or so. At 10 to the 14 watt per square centimeter, and that this plateau stayed for about 20 years, in fact, 65, 85. The power of the intensity was of the order of 10 to the 14 watt per square centimeters. And that, this plateau was due because we couldn't increase the intensity more because of the nonlinear effect that we will describe in a minute. Because then we came up with chirp pulse amplification, and then you know, we could really climb. We could increase more power and power. And so here, what is exciting, okay, is the fact that now we are going to go into this different area, you know, purple, blue, or blue we will go fast, but green and yellow and orange, yeah, quickly, okay. What happened is, of course, because the intensity changes, you are going to change regimes, okay? And here we are in a regime where the electrons are still bound to the nucleus, okay? And then we go into a regime where now the electrons are not going to be bound, but they are going to be relativistic. That is, now they are going to leave the nucleus, okay, and they are going to be agitated at the speed of light. So the mass, of course, of these electrons are going to change, and everything is going to change, okay? And this area, it is the area where we can accelerate particles, with extreme efficiency. Okay. Then we go to the yellow, okay, and yellow line. This is now that not electrons are relativistic, but now the protons becomes relativistic. Okay, and then if we increase, and this is where we want to go. Okay, if we increase even the light intensity, what will happen is when we will focus the beam into nothing, into the vacuum, we will materialize the light. We will break down the vacuum, okay? So this is something that we will actually to demonstrate, and so on. And then if you go higher, then you can even talk about, of course, non-RQED, but QCD as well. Okay, so let's go. The reason why we were not able really to increase, we had to stop at this plateau, is the fact that it was because of what we call this nonlinear index of refraction. And we are in a regime where we at 10 to the 14 or so, not just this, but with the laser very quickly, the index of refraction is not a constant, okay? For the first time, it's not a constant. It is now a function of the intensity, okay? So for instance, if you have a laser beam which is not very smooth, like this one, okay? And if you propagate these beams into, say, the amplifiers, transparent even amplifying material, then what you are getting is you are going to get this filament, very high intensity filaments, and you are going to break down, your component, and you are not going to make, if you are a student, you are not going to make your advisor very happy, okay? Because in optics, elements are very expensive, okay? So that's the reason why we had to work at on below 10 to the 14th to avoid this kind of thing. So and then in order to really go around these problems, we will actually we have to increase the energy of the pulse, so we have to increase the intensity, but we have these problems. So how do you do that? Well, so this is where I thought about this technique of short pulse amplifications, which work this way. I told you that if you have a short pulse, which is produced by an oscillators, you cannot directly amplify the pulse by inner amplifiers because you are going to really damage the amplifiers. So I had the idea before amplifications, to stretch the pulse. To stretch the pulse, you lower the intensity, okay? And you stretch the pulse because short pulses, of course, is composed of very, very a large number of components okay? You go from the red to the blue, okay? And that's the reason why it's short, because you have all these components. And so when the pulse is stretched, and we stretch it by factor 1,000, 10,000, 100,000 now, you decrease the intensity, by 1,000, 10,000, 100,000, etc. And then the intensity is less, so you can go through your amplifier and amplify your pulses, every component. And then once you are done with the amplification, you compress the pulse, okay? Of course, that seems simple, like a student will say, well, why you haven't done that before? Let me tell you, okay? You take a pulse, and then you have to stretch it 1,000, 10,000 times. Fine, okay? Then you have to amplify it 10 to the 10, 10 to the 11 times, okay? And then you have to put it back together exactly. And that is what is difficult. it took us, to do it completely, now systems are really perfect. It took us about 20 years to do it, maybe even more. Okay, let's at the same. Now let's go about some of the application. I will start with the one. I'm not going to say it's going to be the boring one, but it's the one in the UV, which is relatively simple. And this, I'm going to talk about applications in the macro machining, this kind of application, and for surgery, eye surgery. Okay. And why is it good? Why do you want to have short pulses to have precision machining? Well, if you have a very long pulse, you see that as you send your long pulse into a material here, you are going to heat up a large volumes around the spot, right? So it's not very desirable if you want to do a very precision machining. If you go to pulses which are nanosecond, which is quite short, but it's not short enough for us. If the pulse, so then you see you have this heated zone will be much less. So it will be better, okay? But if you go to even shorter pulses, then what happens, you will be able to deposit the energy without really increasing the temperatures here, okay? Because the temperature doesn't have, the laser moves a little, the laser in femtosecond regime, the laser moves typically micrometers, okay? A micron. So the heat has no chance, to catch up. So it will be a very nice clean job. So so here if you have, for example, nanosecond pulses, you see you're creating a mess, okay, on your surface, okay? Very ugly, okay? But if you are using short pulses, well, you see then your pulses are pristine now, okay? And also, you don't, it can be anything. It can be ceramic, it can be glass, it can be metal, it can be anything, okay? And it can be anything because nothing really can withstand the power that we can produce, okay? Anyway, so, okay, and one thing also which is very nice is the fact that we can really now, if the material here is transparent maybe like your cornea, okay? Well, you can focus the beam in this transparent bulk material, and if you raise, you can really produce, you can break down the material exactly at the central part of the waist, the beam waist, okay? So you can create a void here, okay? And very clean because heat has not the time to propagate. And of course, this led to this very beautiful application, which is ophthalmology, femtosecond ophthalmology, which was, I wouldn't say invented, but discovered, I would say, by accident in my laboratory. But anyway, so here, for instance, is the pulse can come and focus on the cornea. And on the cornea, because the pulse can go at very high wave rate, okay? You can poke small holes, next to each other, do something like that. So you can generate a flap. And a flap is very, very important. This is what you want to do if you want to correct for myopia, for instance, Then you have to produce flaps. I'm not going to go in detail. But so you see it's very, very clean. Very clean. And now you have this procedure is applied to about 2 million eyes a year, And I was learning, I had a visit from a Chinese scientist. He said that I was a hero in China, because in China, 70% of the population is Maya, you know, and so they love this. Anyway, good. So now what we are going to do, we are going to move to this green one, which is, we will see, is fascinating, okay? In this green one, what happened is, you see, in the reason why you emit light, or you're sensitive to light, is the fact that the atoms, when it's limited by light, the atoms, you know, which is composed of nucleus, you know, and electrons, they are agitated, they are moving because of the electric field of the light, okay? But the motion is not very fast, okay? The frequency is fast, but the motion is not very fast, okay? But now, which is much less, when I say not very fast, much less than the speed of light, okay? Now, if I'm using light, this type of light I described, and I shine atoms, the electrons are going to move large amplitudes, but they will move now at the speed of light. And this is just, that's the first, so only formula you are going to see, because I mean I know excellence is not. I say that I'm not going to have quiz after the talk, okay? So here, for instance, you know that's an electromagnetic wave, light, okay? And when the light is as low intensity, like this light that you are produced by the lamp here, you know, really the amplitude is not very large, okay? And the light, you know, propagates in we said propagation directions, okay? And the electrons are moving perpendicularly to these motion directions. Now, if now the electrons, you know, now are moved at the speed of light, what happens is, this is really the force which is applied to the electrons, okay? Normally, you know, for optics in general, you know, F equals QE. We neglect this term, which is V over C cross B. Because why? Because the velocity of electrons is much less than the speed of light. So this term is negligible, okay? But now with high intensity laser, this term now is as big as this one, V equals C. And on top of that, so the electrons now are not going to move perpendicularly to the propagation direction, but they will move parallel to propagation direction, because the V cross B gives you a force which is parallel to the propagation directions. So this, of course, optics change completely, okay? Now let's look at the different, we are going to see now that changes that open up, we'll see that we will be able now to accelerate particles, and that will open up new applications and so on. Okay, so I'm going to say, we are going now to use the light to accelerate lasers, okay, to accelerate particles like electrons, okay? Now, this concept was in fact discovered by my good friend Tajima. You know, it's called the Wakefield Accelerations. And he works this way. And you will see that it's an incredibly powerful concept. So if I have my laser here, my CPA laser, what I can do is I can focus the beam into this gas jet. Okay, very small gas jet, about 1 millimeter in size, nothing. Okay, and now this point, what happened is the laser is going to generate a plasma. That means the electric field of the laser is going to ionize the ions, which means it separates the electron from the nucleus. And so now you have a plasma. It's kind of a soup of electrons and protons, okay? And so, and this, you can make a plasma wave, very much like a wave on the sea. And the electrons are going to be like a surfer, will be trapped by this wave. So here you have this short pulse, and the short pulse, is, as I say, in space is about millimeters, not micrometers, I'm sorry, and making this wave, and behind you have these electrons which are really captured by the wave. And the electrons are now accelerated at nearly the speed of light. The electrons can acquire really a very high energy. Typically, we say that's about GeV per centimeters. GeV, giga electron volt, is a large number in accelerations. Per centimeters is enormous. If you want to do that, a GeV, if you want to produce GeV particles, well, you will have to have something like this, which of course is much less attractive than this, okay? So you will have something like this, very, very complex, very long, because that's a GeV you've seen. Basically, there's a fact with conventional systems, it's basically GeV per about 100 MeV per centimeters. Okay, 100 MeV per centimeters. So this is about laser is about 10,000 times more efficient. Okay, so that is. Right. So here, for instance, if I take the LHC, Large Hadron Collider at CERN, the particles are accelerated to TeV. Okay, and because you are using radio frequency, to accelerate your particles, radio frequency is 10 to the 9 giga electron volt, gigahertz, I'm sorry, 10 to the 9. And the light is 10 to the 15, you see. You are going to accelerate your particle, as I said, about 100 MeV per meter. So if you want to go to the TeV, well, it takes 27 kilometers, okay? Now, if you do that, if you will do that with lasers, it will be something like 10,000 times shorter, okay? Which means something like meters, okay? So this is, of course, very, very exciting. And right now, so here it would be like a football field or something, okay, if you are using lasers. Now, we are working on something else with Toshi Tajima, and we said, okay, if we were able really to produce very short bursts of X-rays with the high amplitude, then the gas that we will really use will not be a gas, it will be a solid. Because the X-ray goes through the solid. And then, but the the electron density is almost 6 orders of magnitude, higher. So you should be able already to produce now, gradients of TeV per centimeters, which means we will produce TeV particle on the top of the fingers, as opposed to these 25 very large systems. Now, that's one thing. Of course, when we accelerate these particles, in femtoseconds, we take a particle and we take it, to the speed of light with gammas of hundreds. Okay, and of course, it involves an incredible acceleration. Okay, and so if you think about the equivalence principle, by Einstein again, okay, which says that gravity and accelerations, are the force gravity with the force due to gravitation, they are equivalent, okay, which means that if you are using this type of accelerations, then it will be really something which will be first will be observed in we will have effect that you only can only black hole can produce. So you will have this type of accelerations in black hole of something like 1,000 times the solar mass. Okay, and so this is very exciting because you are bringing cosmology into, you are inviting cosmology, in your laboratory now with a laser. So that is really exciting. Okay, now I'm going to go into a new application which is very important, is this proton accelerations. And you will see that protons, especially when they are relativistic and so on, have many applications, very important, and including societal applications. So for us to accelerate protons into the relativistic regime, it's very simple, okay, because we have these very high intensity lasers. So we take a thin films. We are focusing this laser on the thin films, and then immediately what you do is you Okay. What you do is, of course, you have this thin film is composed of electrons and protons and so on, but electrons are bound to the protons. But anyway, the intensity is very high, so you're ionizing the atoms. So you have the electrons which are pushed by a very strong ponderometric force of your laser, okay? And behind, you leave behind the protons, which are very massive. So you separate the electrons from the protons, and so the electron after that attract the proton behind, okay? And this proton can have energy in giga electron volt. And this is phenomenal, because once again, if you want really to produce proton in the giga electron volt, this is what you have to build. And that is extremely big, extremely expensive, okay, as opposed to this very thin film and, of course, a short pulse laser. So now, the shorter the pulses, the better it is. Okay. What, for instance, for medical applications, what you want, are really protons in the GeV regime. The GeV regime, the protons are relativistic. Okay. And you can show that if you have a pulse, which is short, but not that short for us, but 30 femtosecond, pulses are composed of 16 cycles, 16 optical cycles. Okay. And then if you are using pulses with one cycle, single cycle, then you see that now you can produce protons with energy of over a GeV very easily. Okay. So this is very, very important. This is one of the big areas where we are working now because of the applications in medical. So now if you have really high energy protons, there's a number of things that you can do. That's one thing which is important, is a proton therapy. Okay. If right now, if you are using X-rays or electrons for therapies, so you are going to focus your beam on the tumors, okay? But the problem is you are going you will burn the tumors, but also you will affect all the tissues which are before the tumor, okay? So it's not, people are using it, but it's not great. On the other hand, with protons, you are focusing your beam on the tumors, and you have what we call the Bragg peak. I'm not going to get into these details, but you can adjust the distance where you are going to deposit the energy exactly where you want it. And you are not going to affect the tissues, the healthy tissue in front. So this is really the therapy of choice. The problem with this therapy is extremely expensive. You want to build, there is center for proton therapies, but they are very, very expensive. They are big, of course, and very expensive. And so, of course, our dream is to do that with the laser, okay? Because we could produce these protons at high energy, where you want to be, and use them, for this type of application, which are, of course, enormous. And then you have other applications, in this nuclear regime, where you can make radionuclides, okay? And basically, near the bed of a patient, you don't have to produce them in a reactor far away, but you can produce them in the hospital, for instance, okay? And then you can use them, and you burn the tumor this way with this. And of course, you can use nuclear activity for radioisotope for imaging, and diagnostics. So this is just a few examples. Now, another very, very important application of high energy protons is transmutations, trying to clean up the nuclear waste, okay? And you know that we have, of course, tons of nuclear waste in the world, okay? So, we're using uranium, reactor uranium, and so we are producing neutrons, which is produced by the reactors. And what happened is, of course, with this neutron, you want to fission, this nucleus to produce the energy, okay? But doing that, you can, from time to time, okay, here you fission, right? You take the the neutrons, and you fission this nucleus, and you have some fission product. And the fission product are not bad. I mean, they live not a long time. Okay, so this is okay. But if sometimes the nucleus captures the neutrons without fissioning the nucleus, then you are making new elements, which we are calling that Transuranian elements, which can live really literally forever. Okay, and forever meaning 50,000 years up to 1,000,000 years. Okay, and of course this is the one that we want really to get rid of. So what we want to do, one thing we want to do is to trying to transmute this material. So if you have, for instance, one of these elements, which is Neptunium, you have Curium, Neptunium, Americium, and Plutonium, like that. And so take your, what you want now is really to take your neutrons, which is produced by the laser, okay, and you use the protons, if the energy is high enough, to really to fission your nucleus. And the nucleus, as I said, you're making new product, but they are not that bad, okay? The lifetime is about, for this one, 11 minutes, this one, 21 hours. I mean, it's pretty fast. So this is one thing that we do. The other application, I don't have a slide for this, but is by using, we have to think about using thorium instead of uranium, okay? Because there's a lot of, I'm not going to get into this story, but so if we want to try to use thorium, we need to, we want also to use the thorium like in the conventional reactors, which could be critical reactors or what we call ADS reactors, which is subcritical reactors. That is, now we could use the thorium with conventional reactors and accelerators, which will provide the accelerators these neutrons at the right energy, okay? And these neutrons will really fission the bad stuff. So I'm not going to get into this area, unfortunately, because I love it. Now, the last applications that I'm going to talk about is the space. The space is because, since 1957, okay, when we had the first Sputnik was sent, okay, we have sent a lot of debris in space because every time when we launch satellites, we are producing debris. You may have seen the movie Gravity, okay? So this debris right now, all kind of debris, the size of debris of meter size or millimeter size. And they travel at 50 times the speed of the fastest bullet, okay? So even a small debris, can be very dangerous. And you have millions of them now. So it's time now, we need to do something, okay, about it. And so right now, we sent, since 1957, we sent the equivalent of 4 times the Eiffel Tower. Okay, so 28,000 tons of stuff in space. And about half Eiffel Tower is still circling around, And this is, of course, something that we won't try to address. We won't really to. Also, big debris, they do have ways to do it, but the small one, the millimeter size one, are problems. And what we propose, I hope I will have it, is to do it by using lasers. Here we are seeing an experiment which was done by Chinese, where they blew up a rocket, and then they generated tons of particles. And so we want to try to use a new type of lasers that we are developing at the École Polytechnique, which is called ICANN, to really get rid of these debris. But the way we are going to do it, the way we want to do it is not to blow up the debris, but to tickle the debris, and make a plasma, makes a rocket, by doing that. And this rocket, the plasma, is going to produce a rocket effect. And this debris will be moved, deorbited, and will go hopefully in the atmosphere and will get burned in the atmosphere. So that is that's the plan, okay? So now, oh, Jesus, again. So now, I gave you an idea of the type of things we can do with high intensity lasers. You see that there's enormous amount of applications right now. And so it's a very active medium. Now, and I think, I concluded by saying that I show you many, but there is more to come, okay? And so I want to thank Ørsted because, laser is a direct application of the work of Ørsted. Now, one thing I want to talk about is about when you win the Nobel Prize, what happened? Usually, I'm ahead of you because usually the students, ask me this question, so I'm preemptive. So when the thing that you do, you are invited to Stockholm and to stay for about a big week, and the first thing you have to do is to give a lecture, lecture of what you have done. It's a big lecture, big auditorium, 1,500 people or so. So you give that. And the second, then, you have to learn how to receive the prize. So you spend the morning, before how you can get the prize from the king and so on. So one lady here, is really acting as a king, and you have to learn and so on. So the whole morning we are doing this. Well, because we are about 10 people. And once you have that, when we rest a little bit with Donna, and then it's time for the ceremony. Where you have to be all dolled up and so on. We have Marcel here and Donna. And then you have the ceremony itself. So the ceremony is, you have all the laureate here, okay? So, you have usually 2 or 3, up to 3 in physics, in chemistry, in medicine, and then after you have in literature, and pay the Nobel Prize for Peace. And so here we are, here, okay, waiting our turn. I'm the first one here because physics is first, okay? Physics is first when you go to the... But for Nobel, it was that's the way. Okay. And so then you get the prize, okay, from the king. Then you are very proud. And so here are all the Nobelists. And then you are congratulated by your wife. And then you have this banquet of 1,500 people. Amazing, absolutely amazing. Where you have, of course, you have music and so on, dance and so on, very, very bad. And we are, of course, the laureates are in the center, and especially the physics one, who are exactly in the center of this big table, And, I told you that the physics is number one. Plus, if you are a woman, you are number one, so you are next to the king, okay? And so if you have number two, you are next to the queen and the Princess Sophia here. And it's very nice, no? The Swedes are doing that beautifully. And, but what is the most, of course, a lot of glamours, of course. But what is the most exciting moment, really, in all this, is this one. This one is when the last day, you are asked to come to the Nobel Foundations. And so you have some paperwork to be done and so on. And then you are in this, they take you into this office, nothing special, okay. But they come with some notebook, I would say, it looks like a notebook, nothing much. And you, especially what's special about this notebook is they have a signature for all the Nobel Prize. And they ask you to put your name on it. And that's very emotional. It is very emotional, and I'm really pleased to see that we have Marcel with me. And that's why I like these pictures, because the Nobel Prize was not just me, but it was also a lot to Marcel, which helped me for 50 years. Can you believe that, staying 50 years with a physicist? What is worse than that? So she really needs all the, all the thanks possible. And I guess I'm going to stop here and thank you very much.
Professor
So
Mourou.
now it's your turn.
Professor Mourou, you're excellent. Thank you for an excellent and inspirational lecture. One might even be tempted to say an extremely enlightening lecture. My name is Thijs Wegge. I'm a professor at DTU Energy, a member of the DTU Ørsted board, and I have the pleasure of coordinating this Q&A session. So it's an extreme honor and also a unique opportunity to have you here on campus, in particular in these special times. But as you might have noticed, we have a few less students, faculty, and guests in here today than we do normally. But fortunately, many are joining us virtually. And so we will start the questions in the auditorium. But if you're following us on YouTube, you can ask a question using the chat function. And I'll do my best to convey it to Professor Mourou. And hopefully we can have a lively discussion. Before we start, when you get the opportunity to ask a question, please state your name and affiliation first, so we know who Professor Mourou is talking to. I think we'll start with the first question in the auditorium. Possible? Thomas?
Yeah, I'm Thomas Bjørnholm. I'm the Director of Research at the Willum Foundation. And I've worked a long time at the University of Copenhagen, also with free electron lasers and synchrotron radiation. And my question is, can you try to relate the development you have described to the development with the free electron lasers?
Yeah, we were talking about that for lunch, I think. Right? For lunch. Yeah, we really want to, of course, to produce coherent X-rays. Okay, because that's the name of the game. Okay, to produce coherent X-rays for free electrons, but we have a novel scheme based on high intensity, and the scheme is the following. I just trying to summarize it because it's difficult to explain it like this. But it's really to compress. You have seen that we have a pulses which is composed about 10 oscillations. Okay. Each oscillation is 2 femtoseconds. So you have a pulse which is about 30 femtoseconds, and which means you have about 30 cycles. So we have now a technique really to produce a single cycle. But the single cycle, of course, is invisible. What you want to do now is try to compress it to be in the X-ray regime by a factor of 1,000. And what we do to compress the pulse, we are using a technique that I call relativistic compression. So relativistic compression works this way. If you have a mirror traveling at the speed of light, okay? If you have a beam, which is of course traveling at the speed of light, okay? So this beam is impinged on the mirrors, and the reflection is also going at the speed of light. This first beam is high intensity, and when it's focused on the target, which is simply a metallic target, it can be even a dielectric target, a thin. The beam is focused, and the intensity is immense. Okay, it's typically in 10 to the 21, 10 to the 22, 23, which means that the ponderomotive force is very large, ponderomotive pressure. So you are going to, like I showed a little bit, to take the electrons, and push the electrons, in front. And of course, the ions are going to stay in back. And in a process, you are going to generate a very large DC field, huge DC field. And this DC field will take the electrons and will bring them back. Okay, so you will take the electrons which are mirror and will bring them back at the speed of light with gammas of 1,000 something, okay, in thousands, which means that you can compress the pulse by 1,000. Okay, if you have relativistic mirrors, you have a beam going into these mirrors, reflected, you see that, as I said, this one is moving at the speed of light, mirror is moving at the speed of light, reflected mirror is moving at the speed of light. You compress the pulse by a gamma factor. So now if you go, you have now a way to go from the visible, put your energy. So you go from femtosecond, because the visible cycle is femtosecond. If you compress it by a factor of thousands, you go to the attosecond. The attoseconds is X-rays. Okay? So, and this X-ray pulse is a single cycle also. Okay? Single cycle with energy, because it's relatively efficient. Okay? So now we have simulation where we can show that we can go even to zeptosecond, because we can compress the pulse so much. But it could go up to zeptosecond. But if we stop at attosecond, I'll be happy. Okay. don't want to be greedy. But you see the idea. So with the idea, which is really, I think, is very complementary to the free electron lasers. But here in this, it's a way to produce a very coherent single cycle with high energy. Okay. So this is, and short pulses, of course, they are a femtosecond. As opposed to maybe the free electron laser, I don't remember exactly the numbers, but the energy of your free electron laser is what, millijoules or something? Millijoules, right? And the X-rays are keV. keV, yeah. So it's very comparable. And the length, the pulse length, is maybe 50 femtosecond, yeah, which is very long. So these are the type of things, which we want really to do with extreme light. Okay, and we are working on this. Very, very different, but the objective is the same. We want to produce coherent X-ray pulse. Yeah.
Thank you. Question more? Are there more questions in the auditorium? Please.
By the way, I want to say one thing. I would like if a woman could ask the questions. I would like really to have the ladies, not just the men. But please, ladies, ask me a question.
We give them a chance to talk while Martin asks.
Thank you very much.
Go ahead.
Martin Nielsen, DTU Physics. I just had a thought when you were discussing this relativistic mirror. Is there a fundamental limit to how short you can make the pulses?
Yeah, but I don't have the time really to go through that. Yeah, there is limits. Yeah, there are several limits, in fact. Yeah, but it should work in a regime of gamma regime of 1,000 to 10,000.
Are there more questions in the auditorium?
Mm-mm.
We do have one.
I'm Chen Jiachen from DTU Chemistry, and what I want to ask is, what's the energy efficiency for the process to produce such high energy lasers? And
efficiency for what?
For the whole process to produce such the laser.
Because CPA efficiency is very large.
And
I mean, 80%.
Another question about the
70%.
application is how much energy we need to mitigate the nuclear waste and compare with the energy generated from that nuclear fuel? Yeah.
Well, I mean, we don't have all the right now. I mean, the laser are still not. It's not so much the energy. The energy per pulse we have it. It's a rep rate. Okay, which means the average energy. Okay, but we still don't have it. We are at a kilohertz right now. Okay, we need more like 100 kilohertz or so. Okay, and the efficiency also. I mean, we are pretty good now in terms of efficiency. But if you want to try to do commercial systems, something which is very, it's not enough. We have to improve that. But we have ways to do it. Yes, lady.
Hello again. So my name is Jane Volbeck Nielsen. I'm head of department at DTU Physics. Thank you very much for a fascinating talk. I will ask a question about the non-physics part. So we've heard interesting examples of how you transfer fundamental physics knowledge into innovations, medical applications. How do you see the best way of doing that? It's not always that easy. It seemed very smooth.
Yeah,
today.
when it's done, it looks like very smooth.
It does always, right? How does that happen, and how can we strengthen this transition?
I don't have a really easy formula to ask. You know, of course, what you have to have. I mean, for me, in my groups, you know, usually I had, you know, relatively large groups, and in a group, you know, you have a mix of researchers and of graduate students from engineering to basic physics. Also, but you know, you never know. I mean, because I was paid by NSF to do physics, and we did a very important application in medicine. You know, so what you have to, that means is what is that you have to be ready. You know, and I was, you know, I was getting my money from. I don't want to invite you to become to be cavalier with your grants, but the money I was getting, you know, was for physics, and I used it for medical applications. So you have to have, you know, of course, when you do this, depending how you people, NSF and so on, in Denmark are willing to accept that. Because sometimes, especially at the beginning, you know, when you have not done it, or of course now it looks like of course you have to do that. But at the beginning, it's not like this. So I think I was also, the reason why we did it is because I was at the University of Michigan. And at the University of Michigan, the presidents and all the provosts and so on were very helpful with trying to transfer. You know, they were very, very helpful. That's the reason was I was saying my students was when we had this accident, you know, we had to close the lab. So, and before we did that, I mean, we had a meeting with the president and all the deans. And so we described how that happened, because an accident like that is very serious in the States. I mean, everywhere, but in the States it's pretty serious. And so we showed, you know, what happened and some of the results and so on. We didn't have much result, just not much, okay. But they went and deliberated, and when he came back, Jim Dudestert was the name of the president. He said, "Okay, Gerard." I said, "Okay, now we are going to close the lab." What was decided is that we will give you $500K to continue this work instead of closing. So, you know, maybe I don't recommend maybe to go for that. You know, it doesn't work all the time. Okay, but I mean, depends a lot on your, I think, on the management. You know, I'm sure here it will be easy.
We have one more question in the auditorium.
Yeah, I don't know if you can reach me, but yeah. My name is Nini Bulta, I'm professor at DTU Energy. I have a question. You show a very interesting roadmap. And we are now at about 2020, not about 2020, and you show that we are going to reach 2030 with some values.
Okay.
What are the physical challenges reaching this?
Well, okay, very good question, of course. So right now, you know, of course, we try to get the highest intensity or highest peak power. Power is energy by time. So right now, because energy in a laser system, the size of lasers is proportional basically to the energy. Okay, and right now we have a system with 100 joules. This system with 100 joules are enormous already. Okay, and very expensive. Okay, And I don't think we can go for the megajoule or something like that. You know, it will be too expensive. I think so. So that's the reason why we are working now on trying to pulse compress to reduce the size of the pulses, the duration of the pulses. So instead of increasing the energy by a factor of 1,000, I prefer to decrease the pulse duration by a factor of 1,000. And so this is the reason why we are working on this concept using relativistic mirrors and so on. And as you compress the pulse, of course, you compress the pulse and you go from the visible to the X-ray automatically, you know. And so then it's interesting. So now the pulses are going to be short. This intensity will be in the X-ray regime. So we will have now very, very high intensity in the X-ray regime. Okay, so we can do a number of nonlinear effects in the X-ray regime. So but also we could use for like all the applications of FEL and so on. You know, we know a lot of these applications. But also what we could do is, because we have X-rays, so we can focus the beam to a smaller spot. We have shorter pulses. So we could go to the Schwinger field, where really vacuums becomes matter, or light becomes matter. And that, of course, we are exciting about that. Yeah. But, yeah.
One more question in the auditorium.
Thank you very much for a very inspirational talk. My question is actually related to the last question from Professor Chris. My name is Peter Jebsen, and I'm professor at the Department of Photonics Engineering. But the question is related in the sense that once you have this enormously short pulse, you spread your energy out over the whole spectrum.
Mm-hmm.
So is there a fundamental difference in studying these high energy phenomena, whether you have, let's say, 1 femtosecond pulse with a certain amount of peak power, or the same energy compressed into an attosecond, so that you spread the energy out over much further spectral range, so that you may, hit more resonances than you would with a more narrow spectrum and something? Is there like a trade-off there? What is better, to increase the energy or decrease the pulse length?
There's no way that you can beat, the Heisenberg principle.
Sure.
If you really shorten the pulse, well, you have to accept the fact that you are going to broadband. But this is something that we do all the time. This is when in the laser systems, I remember when we were working with very short pulses, we started to work with picoseconds and femtoseconds. People were saying, yeah, but what is this? You are going to have very broadband and so on. No, because usually the effect that you are really studying, the bandwidth is the same, or even broader. So we never had this problem. I don't think we are going to. No. You see what I'm saying, right? See, because the effect. If you look at nuclear physics, for instance, the transitions, can be extremely fast. Femtosecond can be, it's a lifetime for them. Okay. Attoseconds and so on. So it depends what you are looking.
So if the process is fast enough, it doesn't matter?
Doesn't matter. Oh no, what you are observing, I can accept it. Yeah.
I think we'll take one question from cyberspace here. This is from Abbé Petit from DTU Photonics. Thank you, sir, for the talk. Can you elaborate why protons will not damage the tissue before the tumor cells?
Oh, this has to do with a very well known effect, which is called the Bragg effect. Okay, where the protons, deposit their energy. They deposit all their energy especially in the Bragg distance. Okay, it has to do. I mean, it's something that it's well-known effect. Okay, yeah.
And maybe I'll take the last question. I know you're still very active in the lab. What do you
Not in the lab. You see where I am now. Should be in the lab.
What do you see as the big next challenge for yourself in the field?
Oh, definitively what I want to do is, keep saying that, is produce power, energy, without destroying the planet. That's what I want to do, and that's the reason why I mentioned I did not have the time to talk about thorium and so on, but I'm looking at ways, the transmutation first, and then trying to find new, trying to move from uranium to something which is, I think, is much better, is thorium, where we don't have all these problems of nuclear waste and so on. Plus, we have much more thorium than uranium. So we can feed the planet for about 20,000 years. Okay. So, I mean, of course, when you go outside, you see a lot of windmill and so on. But I think if we really want really to produce the energy for the planet, we have to go nuclear. And so this is, so I know this is not popular to say that, but I hope we'll be able already to, if you do the right thing, I think that's the way to do it.
Well, if you want to make nuclear safe, then maybe we shouldn't take too much of your time.
Because I don't have the time. I'm working to the, yeah, very good.
With that, I think we should all thank Professor Mourou for an excellent and inspirational lecture. And today, unfortunately, there is no reception afterwards because of the COVID restrictions. Mm-hmm. So thank you all for your participation, both virtually and in reality. And again, thank you all for joining us today.
Thank you, everybody, for listening.